the surprisingly simple soil amendment that dramatically increases productivity. Modern agriculture is obsessed with complexity. Precision maps, satellite imagery, variable rate application, AI-driven recommendations, predictive models that promise to forecast yield before the seed even touches the soil. And yet, despite all this sophistication, many producers face the same frustrating reality year after year. Yields plateau, input costs rise, and margins shrink. This contradiction is not accidental. It is structural, because while attention has shifted upward toward data, software, and machinery, one foundational element has been quietly neglected. Something basic, something old, something so unglamorous that it rarely makes headlines or marketing brochures. The soil itself, more specifically, the chemical balance of the soil, and within it, a single factor that quietly controls nutrient availability, root development, microbial activity, and ultimately, plant productivity. Most farmers believe they understand it. Many test it, few truly correct it properly. And that misunderstanding is costing productivity. For decades, soil fertility discussions have been dominated by macronutrients: nitrogen, phosphorus, potassium. Entire management strategies revolve around them. Application rates are calculated down to the kilogram. Timing is debated endlessly. Products are reformulated, coated, stabilized, enhanced. Yet all of this assumes something critical: that the soil is actually capable of making those nutrients available to the plant. Often, it is not. The reason is deceptively simple. Soil acidity, not in the dramatic, crop-killing sense that triggers immediate alarms, but in the subtle, chronic form that silently limits performance season after season. A soil can contain adequate levels of nutrients on paper and still behave as if it is deficient in the field. Roots struggle, microbial activity slows, certain elements become chemically unavailable, locked away despite being present. Producers respond by adding more fertilizer. Costs increase, returns do not. This cycle repeats so often that it has become normalized. What is rarely acknowledged is that many of these fields are not suffering from a lack of inputs, but from a lack of correction. Specifically, correction of soil pH. pH is not a nutrient. It does not feed the plant directly. It does not show up in yield maps as a flashy variable. But it governs everything beneath the surface. When soil pH drifts out of its optimal range, nutrient efficiency collapses. Phosphorus becomes fixed. Calcium and magnesium imbalance root development. Aluminum toxicity increases, restricting root elongation long before visible symptoms appear above ground. The plant survives, but it never thrives. This is where the story becomes uncomfortable. Because correcting soil pH is not new knowledge. Agricultural science has understood this relationship for over a century. The solution has existed for generations. And yet, it remains one of the most poorly executed practices in modern farming. The amendment in question is not a breakthrough product. It does not come with proprietary technology or premium branding. It is lime, agricultural limestone, calcium carbonate, sometimes dolomitic, sometimes calcitic. Cheap, abundant, unremarkable. And when applied correctly, transformative. But, applied correctly, is where most operations fail. Many producers lime reactively, not strategically. They apply uniform rates across fields with highly variable conditions. They treat lime as a maintenance input rather than a structural correction. They underestimate the time required for it to fully react in the soil profile. Worst of all, they expect immediate results. Lime does not behave like nitrogen. It does not produce visual responses in weeks. Its effects unfold slowly, methodically, as chemical equilibria shift and biological systems respond. This delay causes skepticism. Farmers apply lime once, fail to see dramatic short-term gains, and quietly deprioritize it. The practice becomes irregular. Rates decline. Fields slowly acidify again. Meanwhile, yield ceilings remain unchanged. What is rarely discussed is how profound the long-term impact of proper liming actually is. Correcting soil pH improves nutrient use efficiency across the board. It enhances root architecture, allowing plants to access deeper moisture and nutrients. It stimulates microbial populations responsible for mineralization and organic matter cycling. It reduces the need for excessive fertilizer applications by making existing nutrients available. In other words, it amplifies every other input already being used. This is why the effect on productivity can appear dramatic, even though the amendment itself is simple. The soil stops fighting the crop. But simplicity should not be confused with ease. Effective liming requires precision. It requires understanding buffering capacity, cation exchange, base saturation, and the difference between surface correction and profile correction. It requires patience and planning, often over multiple seasons. This is where many operations hesitate, because the return on lime is not always immediate, and modern agriculture has been trained to chase fast feedback. However, when productivity gains are analyzed over a longer horizon, fields with properly corrected pH consistently outperform those without. Not marginally, structurally. The question is not whether lime works. The question is why such a foundational practice remains so poorly executed in an era obsessed with optimization. And that question leads to deeper issues in how soil is evaluated, how recommendations are made, and how short-term decision-making overrides long-term performance. In the next part, we will examine why most soil tests are misinterpreted, how this leads to incorrect liming strategies, and why average pH is one of the most misleading metrics in modern agronomy. That is where the real mistakes begin. Why most soil tests lie and how that sabotages liming decisions. Most producers trust soil tests. They collect samples, send them to a lab, receive a report filled with numbers, charts, and recommendations, and assume they are looking at an objective diagnosis of their field. In theory, this makes sense. In practice, it is where one of the most damaging misunderstandings in modern agronomy begins. Because a soil test does not show the soil, it shows an average, and averages are dangerous. A single soil test result often represents dozens of hectares, sometimes hundreds. Within that area, pH can vary dramatically. Slight changes in topography, drainage, organic matter, historical fertilization, and even old fence lines create zones with very different chemical realities. When these zones are blended into one composite sample, the result is comforting but misleading. A field might show a pH of 5.8 on paper. That sounds close to acceptable. No alarm bells, no urgency, but within that same field, there may be large areas sitting at 5.2 or lower. In those zones, aluminum toxicity is already restricting root growth. Phosphorus availability is compromised. Calcium is deficient in the root zone. Microbial activity is suppressed. The crop struggles there every season. At the same time, other zones might already be close to optimal pH. These areas respond well, masking the problem elsewhere. Yield maps show variability, but it is often blamed on weather, genetics, or random field behavior. The soil test did not lie outright. It simply hid the truth in an average. This is why blanket liming recommendations so often underperform. When lime is applied at a uniform rate based on an averaged pH, it is usually insufficient for the most acidic zones and unnecessary for the better ones. The field never fully corrects. The worst areas remain limiting factors, dragging down overall productivity. The producer concludes that liming did not make much difference. In reality, it was never allowed to. There is another layer to this problem, and it is even more subtle. Most standard soil tests focus on pH measured in water or calcium chloride. These values are useful, but they do not tell the full story. They describe the current acidity, not the soil's resistance to change. That resistance is known as buffering capacity. Two soils can have the same pH and require completely different amounts of lime to correct. Clay content, organic matter, and cation exchange capacity all influence how much acidity is stored in the soil system. A sandy soil with low buffering capacity may respond quickly to small lime applications. A clay-rich soil with high buffering capacity may require several times more lime to achieve the same pH shift. When buffering capacity is ignored, lime rates are often underestimated. The pH moves slightly, then stalls. The soil absorbs the amendment without fully correcting. Again, the conclusion is predictable. Lime seems ineffective. But the failure is diagnostic, not chemical. Another common mistake lies in timing expectations. Soil tests are often taken shortly after lime application to check results. This is premature. Lime reacts slowly, especially when incorporated only at the surface. Full pH adjustment, particularly deeper in the profile, can take months or even years. Testing too early leads to frustration and the false belief that nothing happened. The soil, however, is still changing. This misunderstanding is compounded by how recommendations are communicated. Many reports reduce liming to a single number. Apply X tons per hectare. No explanation of depth, no distinction between surface correction and subsurface acidity. No discussion of whether the goal is maintenance or structural correction. The producer is left with a recipe, not a strategy. And agriculture, at this level, does not respond well to recipes. There is also a psychological factor at play. Lime does not feel productive. It does not look like progress. It does not have immediate visual impact. Unlike fertilizer, it does not green up crops or push rapid growth. It works quietly, invisibly, changing the chemical environment that allows everything else to function properly. This makes it easy to deprioritize. Yet when fields are evaluated over longer time frames, a pattern emerges. Fields with properly diagnosed acidity, zone-specific correction, and adequate lime rates consistently outperform those managed with generic recommendations. Not because lime is magical, but because it removes a ceiling that no amount of fertilizer can break. In the next part, we will go deeper into how soil acidity actually limits plants at the root level, long before any visible symptoms appear, and why many yield losses attributed to stress are actually chemical constraints underground. That is where productivity is quietly decided. The invisible root-level damage that steals yield before you see it. Most yield losses do not announce themselves. They do not show up as dramatic yellowing, stunted plants, or obvious deficiency symptoms. By the time something is visible above ground, the damage has already been done. Weeks earlier, sometimes months. This is especially true when soil acidity is involved. Acidic soils rarely kill crops outright. Instead, they impose subtle, chronic stress that limits a plant's ability to express its genetic potential. The crop survives, it just never reaches what it could have been. The primary battlefield is underground. Root systems are far more sensitive to chemical imbalances than leaves or stems. In acidic conditions, the first and most damaging constraint is aluminum toxicity. Aluminum is present in most soils. Under neutral or slightly acidic conditions, it remains chemically bound and harmless. As pH drops below critical thresholds, aluminum becomes soluble. Once soluble, it is toxic to roots. The effect is immediate and severe. Root tips stop elongating, cell division slows, fine root hairs, which are essential for nutrient and water uptake, fail to develop properly. This happens long before the plant shows visible stress. Above ground, the crop may look acceptable. Leaves remain green, growth appears normal in early stages. The producer assumes everything is fine. Below ground, the root system is shallow, compacted, and inefficient. This has cascading consequences. A restricted root system cannot explore the soil profile effectively. Nutrient uptake becomes dependent on what is immediately available in a narrow zone. Water access is limited, increasing vulnerability to short dry spells that would otherwise be irrelevant. When stress occurs later in the season, during flowering or grain fill, the plant has no buffer. Yield potential is lost not because of the stress itself, but because the root system was never allowed to prepare for it. Calcium deficiency compounds the problem. In acidic soils, calcium availability is reduced. Calcium is not just a structural nutrient. It plays a critical role in root membrane integrity and cell wall development. Without adequate calcium, roots become more susceptible to damage and less efficient at nutrient transport. The plant becomes chemically fragile. Magnesium imbalances further disrupt photosynthesis and energy transfer, even when total magnesium levels appear adequate on a soil test. Meanwhile, phosphorus becomes increasingly unavailable. In acidic conditions, phosphorus reacts with iron and aluminum, forming compounds that plants cannot access. Soil tests may show sufficient phosphorus levels, but the crop behaves as if it is deficient. Producers respond predictably. They apply more phosphorus. The additional phosphorus follows the same chemical fate. Costs increase. Availability does not. This misinterpretation fuels the belief that phosphorus efficiency is inherently low, when in reality the soil environment is preventing its use. Microbial activity also suffers. Soil biology is highly sensitive to pH. Many beneficial microorganisms operate within narrow pH ranges. As acidity increases, microbial diversity declines. Processes such as organic matter decomposition, nitrogen mineralization, and nutrient cycling slow down. The soil becomes chemically and biologically rigid. At this point, even perfect weather cannot rescue yield potential. What makes this especially problematic is that none of these constraints are visible in isolation. The crop does not show a single, clear deficiency symptom. Instead, it underperforms quietly. Producers describe these fields as average, inconsistent, or tough ground. They rotate crops, adjust planting dates, change hybrids, fine-tune fertilizer programs, and still see limited improvement. The limiting factor remains untouched. Correcting soil acidity changes this dynamic at its foundation. As pH rises into optimal ranges, aluminum becomes insoluble. Root tips resume normal growth. Fine root development improves. Calcium availability increases, strengthening root structure and nutrient transport. Phosphorus efficiency rises without additional input. Microbial populations rebound, accelerating nutrient cycling and improving soil structure over time. The plant does not suddenly become different. The environment does. This is why yield responses to proper liming often appear disproportionate to the simplicity of the amendment. Multiple constraints are removed simultaneously. What is often interpreted as a good season or better genetics is, in many cases, the delayed result of a soil that finally stopped resisting the crop. In the next part, we will examine why surface liming alone is often insufficient, how subsurface acidity continues to limit roots even when topsoil pH looks acceptable, and what this means for long-term productivity. That is where many well-intentioned liming programs fall short. Why surface liming alone fails to unlock full yield potential. For many producers, liming is treated as a surface correction. Lime is spread, sometimes incorporated lightly, and soil tests from the top few centimeters show improvement. The numbers look better, the practice is marked as done, and yet, yield responses remain inconsistent. This disconnect has a clear explanation. Soil acidity is not confined to the surface. In many agricultural systems, especially those under long-term no-till or reduced tillage, acidity migrates downward over time. Nitrogen fertilization, organic matter decomposition, and natural leaching processes gradually acidify the subsurface layers. The result is a stratified soil profile. The top layer may show an acceptable pH, while deeper layers remain strongly acidic. Roots encounter a chemical barrier as they attempt to grow downward. Above that barrier, conditions are manageable. Below it, aluminum toxicity resumes. The root system stops expanding vertically. From above ground, nothing seems wrong. The soil test confirms good pH. The crop emerges well and grows normally early in the season. But when moisture becomes limiting near the surface, or when nutrient demand increases during reproductive stages, the plant has nowhere else to go. Yield potential collapses silently. This phenomenon is often misattributed to compaction or drought stress. While these factors may contribute, subsurface acidity is frequently the underlying constraint. Surface-applied lime moves slowly. Calcium carbonate has low solubility. Its downward movement depends on water infiltration, soil structure, and time. In many soils, especially those with high clay content, lime may take years to influence deeper layers. Producers expect faster correction because fertilizer behaves differently. Nutrients move, lime does not. This creates a false sense of completion. The field appears corrected on paper but remains chemically restrictive in the root zone that matters most during stress periods. Addressing subsurface acidity requires intention. Higher lime rates, applied over multiple seasons, are often necessary. In some systems, incorporation during field renovation may be justified. In others, patience and repeated surface applications are the only viable approach. The key is recognizing that liming is not a one-time event. It is a long-term structural investment. Another mistake is focusing solely on pH values without considering base saturation. A soil can reach a target pH and still have imbalanced cations. Calcium, magnesium, potassium, and hydrogen occupy exchange sites in the soil. Their proportions influence root behavior, soil aggregation, and nutrient uptake. If calcium saturation remains low, root systems may still perform poorly even at acceptable pH levels. Lime selection matters. Calcitic versus dolomitic sources are not interchangeable without context. Ignoring this nuance leads to partial correction and partial results. There is also a timing issue that undermines effectiveness. Liming is often scheduled around logistical convenience rather than agronomic impact. Applied too close to planting, it has little time to react. Applied without moisture, it remains inactive. Applied inconsistently, it corrects unevenly. Each of these choices reduces return on investment. And yet, despite these challenges, producers who commit to correcting the full soil profile see consistent patterns. Roots grow deeper. Crops handle dry periods better. Nutrient efficiency improves. Yield variability across the field decreases. The soil stops behaving like a series of chemical traps. This is not theoretical. It is observed repeatedly in long-term field data. But it requires a shift in mindset. Liming is not about chasing a number. It is about rebuilding the chemical foundation that allows roots to function without resistance. In the next part, we will explore why many producers underestimate lime rates, how fear of overliming leads to chronic undercorrection, and what long-term data reveals about economic returns. That fear is one of the most expensive habits in modern agriculture. The costly fear of too much lime, and why undercorrection is the real risk. There is a quiet anxiety surrounding lime. Producers rarely say it outright, but it shapes decisions every season. The fear is simple. Apply too much, waste money, create imbalance, cause harm. Lime is viewed as something that must be used cautiously, conservatively, almost defensively. This fear is understandable. Unlike fertilizer, lime does not promise an immediate payoff. It ties up capital, it demands patience, and its effects are harder to isolate in a single season. So rates are reduced, applications are delayed, recommendations are rounded down, just to be safe. The result is chronic undercorrection. Fields hover just below optimal pH for years. Aluminum toxicity is reduced but not eliminated. Calcium availability improves slightly but remains limiting. Root systems grow better, but not freely. The soil improves, but never fully recovers. This middle ground feels rational, but it is where productivity quietly stagnates. Long-term field studies tell a different story. When soils with significant acidity are fully corrected, not partially adjusted, yield responses are not just larger. They are more stable across seasons. Variability declines. Input efficiency increases. The economic return does not come from a single harvest. It comes from multiple years of improved performance. Yet many producers evaluate lime as if it were nitrogen. They ask, what did this do this year? This is the wrong question. Lime is not a seasonal input. It is infrastructure. Undercorrecting soil acidity is like reinforcing a building halfway. It looks responsible. It avoids extremes, but it fails to solve the structural problem. Another factor feeding this fear is misunderstanding overliming. True overliming is rare. It requires pushing soil pH well beyond optimal ranges, usually through repeated excessive applications without monitoring. Most agricultural soils, especially those with moderate to high buffering capacity, resist drastic pH shifts. What producers fear is often theoretical. What they experience instead is the cost of never quite fixing the problem. There is also confusion between maintenance liming and corrective liming. Maintenance liming replaces acidity generated annually through fertilization and biological processes. Corrective liming addresses accumulated acidity from years or decades of imbalance. Applying maintenance rates to a soil that needs correction is ineffective. It slows further decline but does not reverse existing damage. Many operations unknowingly do exactly this. They apply small, regular lime rates, expecting gradual improvement. In reality, these rates barely offset new acidity. The soil remains stuck. Corrective liming requires higher initial rates, followed by maintenance once targets are reached. Avoiding this upfront investment extends the problem indefinitely. There is also a strategic dimension often overlooked. Corrected soils increase the effectiveness of every other input. Fertilizer efficiency rises. Root access to water improves. Stress tolerance increases. This amplifying effect compounds over time. When evaluated properly, lime often delivers one of the highest returns on investment in the entire input portfolio. Not immediately, but reliably. Producers who overcome the fear of adequate rates tend to describe the same shift. Fields become predictable, yield gaps close, management decisions become easier because the soil stops introducing random constraints. The fear of too much gives way to the cost of not enough. In the next part, we will look at how proper liming changes nutrient economics, reducing fertilizer waste and reshaping input strategies in ways that are rarely accounted for in budgets. That is where the financial logic becomes unavoidable. How proper liming quietly reshapes fertilizer economics. Most fertilizer programs are built on compensation. They are designed to offset what the soil fails to deliver. When crops do not respond as expected, rates increase. Products change, additives are introduced, costs rise. What is rarely questioned is whether the soil environment itself is sabotaging those investments. Soil acidity does exactly that. In acidic soils, fertilizer efficiency declines across multiple nutrients at once. Nitrogen losses increase through volatilization and leaching. Phosphorus becomes chemically fixed. Calcium and magnesium remain unavailable when they are most needed. The response is predictable: more fertilizer. This creates a dangerous illusion. Yields may increase slightly, reinforcing the belief that higher rates are working. In reality, the system is becoming increasingly inefficient. Proper liming interrupts this cycle. By correcting pH, the soil's chemical behavior changes. Nutrients already present become available. Applied fertilizer is retained and utilized more effectively. The crop extracts more value from the same inputs. This does not always show up as dramatic yield jumps in the first year. Instead, it shows up as stability. Fields respond more consistently to fertilizer. Variability decreases. Unexpected deficiencies decline. Over time, fertilizer rates can often be reduced without sacrificing yield. In some systems, phosphorus applications can be cut significantly once fixation is minimized. This is rarely planned for. Budgets are built assuming fertilizer demand is fixed. Lime is treated as an extra cost rather than a cost-shifting investment. But long-term data tells a different story. When soils reach and maintain optimal pH, nutrient use efficiency improves year after year. Fertilizer becomes a fine-tuning tool instead of a blunt instrument. This shift has compounding effects. Reduced fertilizer losses mean lower environmental risk. Nitrogen stays where crops can access it. Phosphorus remains in plant-available forms. Calcium supports root integrity rather than being chemically locked. Soil biology amplifies these gains. As microbial populations recover under balanced pH, nutrient cycling accelerates. Organic matter decomposition improves. Mineralization becomes more predictable. The soil begins contributing actively to crop nutrition instead of passively storing inputs. This is where many producers experience a subtle but important change in management. Fields become easier to manage. Response curves flatten. Small mistakes do not carry catastrophic consequences. The system gains resilience, and resilience, while hard to quantify, has real economic value. During stressful seasons, corrected soils buffer crops against drought, nutrient fluctuations, and timing errors. Yield losses are reduced not because the season improves, but because the soil absorbs shock. This is rarely attributed to liming in post-harvest analysis. But it should be. When fertilizer programs are evaluated without considering soil pH, conclusions are incomplete. Inputs are blamed, genetics are questioned, weather takes the fall, the foundation remains unexamined. In the next part, we will explore why the benefits of liming often appear years later, how delayed responses confuse decision-making, and why patience is one of the most underappreciated management tools in agriculture. That delay is not a weakness. It is the nature of the system. The delayed payoff. Why liming rewards patience, not impulse. One of the most misunderstood aspects of liming is time. Modern agriculture is conditioned to expect fast feedback. Apply nitrogen, see greener plants. Change a hybrid, see different architecture. Adjust planting density, see immediate effects. Lime does not operate on that timeline. Its primary function is to alter chemical equilibria in the soil. Those changes propagate slowly, influenced by moisture, temperature, biological activity, and soil structure. In many cases, the full impact of liming is not realized for 1, 2, or even 3 seasons. This delay creates doubt. Producers apply lime, see minimal change in the first crop, and mentally downgrade its value. The practice becomes optional rather than foundational. This is a mistake. Delayed response does not mean weak response. It means systemic change. When lime begins to fully react, the soil profile stabilizes. Aluminum toxicity declines not just at the surface, but gradually deeper. Root systems adjust generation by generation. Microbial populations rebuild. Each season builds on the last. Yield gains may appear incremental, but they stack. This compounding effect is easy to miss because it lacks a clear start and end. There is no single moment where productivity suddenly jumps. Instead, the field becomes more forgiving, more consistent, less volatile. Farmers often describe this as, the field just got better. They rarely connect it back to liming decisions made years earlier. Another factor complicating perception is weather variability. In a favorable year, almost any soil performs reasonably well. In a stressful year, differences become obvious. Corrected soils shine under pressure. During dry periods, deeper root systems access moisture unavailable to shallow-rooted crops. During nutrient stress, improved availability cushions demand peaks. Ironically, it is often the bad years that reveal the true value of liming. But those years are also the easiest to dismiss. Weather becomes the explanation for everything. This reinforces short-term thinking. Agronomic decisions become reactive rather than strategic. Practices that do not deliver immediate gratification are sidelined. Liming suffers most from this mindset. The irony is that patience with lime reduces the need for patience elsewhere. Once the soil environment is corrected, management becomes simpler. Crops respond more predictably. Adjustments work as intended. This reliability has value beyond yield. It reduces stress. It reduces guesswork. It improves confidence in decision-making. Producers who commit to long-term correction often change how they think about their fields. They stop chasing symptoms and start managing causes. This shift is subtle but powerful. In the next part, we will examine why many liming programs fail even when rates and timing are correct, focusing on logistics, uniformity, and execution. Because strategy means nothing if application undermines it. Agriculture improves when fundamentals are taken seriously. If you want more content that focuses on real constraints instead of trends, subscribe to the channel. When the plan is right but the execution ruins everything. Many liming programs fail not because the science is wrong, but because the execution is sloppy. Rates are calculated correctly, timing is reasonable, the decision to lime is justified. And yet, results are inconsistent or disappointing. The problem is not chemistry. It is logistics. Lime is a physical material. Its effectiveness depends heavily on how evenly it is applied, how well it contacts the soil, and how consistently it is distributed across the field. This is where reality intervenes. Unlike fertilizer, lime is bulky, dusty, and difficult to handle. Spreaders vary widely in accuracy. Particle size differs between sources. Wind, moisture, and equipment calibration all influence where the material actually lands. A recommendation of 2 tons per hectare assumes uniform delivery. In practice, some areas may receive far less, others far more. This unevenness creates a patchwork soil environment. Corrected zones improve, under-limed zones remain acidic. Over-limed zones may temporarily exceed optimal pH. The field behaves inconsistently, reinforcing the belief that liming is unpredictable. It is not unpredictable, it is poorly controlled. Particle size matters more than many realize. Finely ground lime reacts faster but is more prone to drift and uneven spreading. Coarser material reacts slowly but stays where it lands. Effective neutralizing value depends not just on chemical composition, but on physical characteristics. Ignoring this leads to mismatched expectations. Another overlooked factor is incorporation. In systems where incorporation is possible, shallow mixing dramatically increases lime effectiveness. Where it is not, reliance on rainfall and biological activity becomes critical. Applying lime without sufficient moisture delays reaction. Dry conditions can leave material sitting inert for months. Timing matters not because of crop stage, but because of soil processes. There is also the issue of field access. Liming is often pushed to, when there's time, squeezed between planting and harvest, or delayed due to equipment availability. Compromises are made. The soil does not care about schedules. Each compromise reduces effectiveness and extends the correction timeline. Perhaps the most damaging execution failure is inconsistency. Liming one year, skipping the next, then applying small rates later does not allow the system to stabilize. The soil oscillates instead of correcting. Consistency is more important than frequency. Producers who treat liming as a long-term program rather than a sporadic task see far better outcomes, even with similar total rates applied over time. Execution also includes follow-up. Without proper monitoring, mistakes persist unnoticed. Sampling depth remains shallow. Zones are ignored. Decisions are made blind. The belief that we already limed becomes an excuse not to look again. In reality, liming is only complete when the soil profile behaves as intended. In the next part, we will focus on how to design a liming strategy that actually works, integrating diagnosis, application, monitoring, and patience into a coherent system. This is where theory becomes practice. Designing a liming strategy that actually works. Effective liming does not start with a spreader. It starts with intent. Most failed programs share a common flaw. They treat liming as an isolated action instead of a coordinated system. Lime is applied, numbers are checked, and attention moves elsewhere. Successful programs think differently. They begin by defining the goal. Not raise pH, but remove chemical constraints to root growth across the soil profile. That distinction changes every decision that follows. Diagnosis comes first. Soil sampling must reflect reality, not convenience. This means separating zones, respecting topography, historical management, and yield patterns. Sampling depth matters. Surface-only samples are insufficient in systems prone to stratification. Without this clarity, precision elsewhere is meaningless. Once constraints are identified, rates must match the problem. Corrective liming requires commitment. Rates should be based on buffering capacity, not comfort. The goal is to reach optimal conditions within a defined timeframe, not to inch toward them indefinitely. This often means higher initial rates followed by maintenance. Avoiding this step prolongs inefficiency. Material selection matters. Choosing between calcitic and dolomitic sources should reflect soil needs, not availability. Neutralizing value, particle size distribution, and consistency between loads all influence outcomes. Cheap lime that does not react is not cheap. Application must respect physics. Uniformity is non-negotiable. Equipment calibration, appropriate spread width, and favorable conditions determine success. When incorporation is possible, use it strategically. When it is not, plan for time and moisture. Monitoring closes the loop. Follow-up sampling should be deliberate, timed to reflect actual reaction, not impatience. Adjustments should be based on trends, not single numbers. This transforms liming from a guess into a managed process. Most importantly, liming strategy must be integrated into the broader system. Fertilizer programs should be adjusted as pH improves. Yield responses should be interpreted in context. Expectations should shift from immediate response to sustained performance. When this integration occurs, something interesting happens. Liming stops feeling like a cost and starts feeling like control. Fields behave as expected, inputs work as intended, variability decreases, decision-making simplifies. This is not about perfection. It is about removing preventable limitations. In the final part, we will address why this simple amendment remains underused, what it reveals about modern agriculture's priorities, and why productivity gains often come from revisiting fundamentals rather than chasing novelty. That perspective matters more than any single practice. Why the simplest fix is often the one we ignore. Modern agriculture prides itself on progress. Bigger machines, smarter software, more data, more precision. Each new layer promises efficiency, control, and higher productivity. And in many ways, it delivers. But progress has a blind spot. It encourages attention upward, toward complexity, and away from foundations. The result is an industry that often tries to optimize systems that are chemically misaligned at their core. Soil acidity is not exciting. Lime does not feel innovative. It does not signal advancement or sophistication. It looks backward, almost primitive. And that perception is exactly why it is underestimated. The irony is uncomfortable. One of the most powerful productivity levers in modern farming is not new, patented, or digital. It is old, abundant, and well understood. Its effectiveness has been proven repeatedly, across crops, regions, and decades. Yet it remains inconsistently applied. This is not a failure of knowledge. It is a failure of attention. Producers are not ignoring lime because it does not work. They ignore it because its benefits are delayed, indirect, and systemic. They do not align with a culture that rewards fast results and visible change. But agriculture does not run on quarterly feedback. It runs on cumulative effects. Every season builds on the chemical and biological decisions of the past. When soil acidity is left unresolved, it compounds quietly. When it is corrected properly, the benefits compound just as reliably. What makes lime powerful is not what it adds, but what it removes. It removes resistance. It removes chemical barriers that limit roots, microbes, and nutrient efficiency. It allows crops to function closer to their genetic potential without increasing input intensity. In that sense, liming is not an additive practice. It is a subtractive one. It subtracts inefficiency. This perspective matters because it reframes how productivity is pursued. Instead of asking what else needs to be added, the question becomes what is quietly holding performance back. Often, the answer is unglamorous. Often, it is already known. Often, it has been postponed. The producers who see the largest long-term gains are rarely those chasing the newest product. They are the ones who systematically remove foundational constraints and then let every other input work as intended. Lime fits that pattern perfectly. It is not a silver bullet. It does not replace good management, genetics, or weather. But it sets the stage for all of them. Ignoring it does not stop crops from growing. It just ensures they never reach their ceiling. And in a world where margins are tight and expectations are high, leaving productivity on the table is no longer a neutral choice. It is a decision. The most surprising part of this entire conversation is not that a simple soil amendment can dramatically increase productivity. It is that, despite knowing this, so many systems are still built on soil that resists the crop at every step. Sometimes progress does not require innovation. It requires correction.